In today's video, I'm going to introduce something new called the Standard Template Library, or STL. And we're going to go through a lot of different little code examples, but I'd like to finish it off with actually performing a linked list on a series of contacts, something that you'd have in your phone contact list or something like that. But before I begin, what I'd like to do is talk about this book here. This is absolutely my favorite C++ programming book. It's called Object-Oriented Programming in C++, but it's only the 4th edition, and it's written by Robert Lafor. And I think it's by far the best textbook I've ever seen for C++. Unfortunately, it's a little bit outdated, and it's missing a lot of the new updates from, for example, things like move semantics and things like that. But in terms of your deep understanding of what are all the moving parts like graphically, I think this is the best book that I've ever come across by far. So it would be awesome if someday he came out and did maybe a 5th edition or just something updated, but for now, this is what I'm working with, and I'm going to take a lot of examples out of this book because it's so good. Most computer programs exist to process data. The data may represent a wide variety of real-world information like personnel records, inventories, text documents, scientific experiment data, and so on. Whatever it represents, data is stored in memory and then manipulated in similar ways. The STL contains several kinds of entities. The 3 most important are containers, algorithms, and iterators. A container is a way that stored data is organized in memory. An array is an example of a container. However, there are many other kinds of containers, and the STL includes the most useful ones. The STL containers are implemented by template classes, so they can be easily customized to hold different kinds of data. And of course, inside the containers, we hold objects. Algorithms in the STL are procedures that are applied to containers to process their data in various ways. For example, there are algorithms to sort, copy, search, and merge data. Algorithms are represented by template functions. These functions are not member functions of the container classes. Rather, they are standalone functions. One of the striking characteristics of the STL is that its algorithms are so general. You can use them not only on STL containers, but on ordinary C++ arrays and on containers you create yourself. Iterators are a generalization of the concept of pointers. They point to elements in a container. You can increment an iterator as you can a pointer, so it points in turn to each element in a container. Iterators are a key part of the STL because they connect algorithms to actual containers, like you can see here in this diagram. A good way to think of an iterator is it's the software version of like a cable that you would plug into stereo components or something like that. A container is a way to store data, whether the data consists of built-in types such as int, float, or even class objects. The STL makes 7 basic kinds of containers available, as well as 3 more that are derived from the basic kinds. In addition, you can create your own containers based on the basic kinds. You might be wondering why we need any kinds of containers. Why not use C++ arrays in all data storage situations? The answer is really efficiency. An array is awkward or slow in many situations. Containers in the STL fall into 2 main categories: sequence containers and associative containers. Sequence containers are arrays, vectors, lists, and deques. And associative containers are set, multiset, map, and multi-map. Instantiating an STL container object is easy. First, you must include an appropriate header file. then you use the template format with the kind of object to be stored as the parameter. So here's an example here. I would create a vector of ints. And here's another one. I would create a list of airtimes. Okay, so these are template, this is template syntax. With associative containers, if I want to create a set of ints, very similar, and you'll notice the angle brackets in here. And then if I want to create a multi-set of employees as an example, this would be the syntax, this multi-set employee in machinists. Okay. Member functions. Algorithms are the heavy hitters of the STL, carrying out complex operations like sorting and searching. However, containers also need member functions to perform simpler tasks that are specific to a particular type of container. So here's some examples of size, empty, max size, begin, end, rbegin, rend. And you'll know they're all lowercase and they are functions. Okay, so for an example, size will return the number of items in the container. Empty returns true if the container is empty. End returns an iterator to the past the end location of the container, used to end forward iteration. So each of these functions actually have a specific purpose. An algorithm is a function that does something to the items in a container or containers. As we noted, algorithms in the STL are not member functions or even friends of container classes, as they are in earlier container libraries, but are standalone template functions. You can use them with built-in C++ arrays or with container classes you create yourself, provided the class includes certain basic functions. So if we look at algorithms, these are a list of algorithms, okay, and we can talk a little bit about their purpose. So for example, find returns elements equivalent to a specified value. Count counts the number of elements that have a specified value. Search looks for a sequence of values in one container that corresponds with the same sequence in another container. Sort sorts the value in a container according to a specified ordering. And finally, I'll look at one, merge. Combines two sorted ranges of elements to make a larger sorted range. Okay, so these algorithms are part of the STL library that you can call and actually do things for you. So I think now what we should do is maybe get into Visual Studio and maybe look at an example of each and every one of these. So what I have here in this particular find function right here on line 12 is I start off with an array and I populate that array, and there is 0, 1, 2, 3, 4, 5, 6, 7. Okay, and with this pointer, what I'm going to do is call the find algorithm. And what I need is the name of the pointer and how far in the pointer I want to go. Okay, so I do have 1, 2, 3, 4, 5, 6, 7, 8 elements, but they are numbered starting from 0 to 7. So what I'm saying is go 8 elements and look for the first time you come to the number 33. Okay, so when I run that, what that ends up saying is the first object with value 33 is found at offset 2. So what I'm saying is 0, 1, 2. Okay, so that's what that algorithm does. Let's take a look at the next one. We're going to look at the count algorithm in Visual Studio. This one is set up quite similar, minus the pointer, but I also want you to notice that we have 33 here, here, and here. So 3 times within this array we have the number 33. And what we want to do with this algorithm is to count the number of times that the number 33 appears. And this is the algorithm that we're calling. And similar to the other algorithm, it was the name of the array plus the number of elements in the array, and then what it is I'm actually trying to count. So what you see here is that when I compile this, it says there are 3 33s in R, in array. So that's how that one works. We'll do 2 other quick examples as well. Next, I'd actually like to go through the sort array in Visual Studio. In this particular example, again, we have an array. Okay, this time it's got negative values. You'll see here -17, -30. And what we're going to do is call the sort algorithm, and it's going to sort the numbers, and then we're going to display the sorted numbers. Okay, so what you would expect to see is that it numerically sorts them from lowest to highest. And all I'm doing is calling the sort function, and then that sorts the array, and then I'm actually going to run this through the display of the array after it's been sorted already. So when I compile this, what I end up getting is -30, -17, 0, all the way to 55. So it worked properly. It actually sorts it from the lowest value to the highest value. Okay, and that's all that that algorithm does. But it's actually used quite commonly. Finally, in this last example, I want to look at the search algorithm. And some algorithms operate on 2 containers at once. For instance, while the find algorithm looks for a specified value in a single container, the search algorithm looks for a sequence of values specified by one container within another container. So let's go to Visual Studio and have a look at that. So here we are in Visual Studio, and we've got 2 arrays. There's pattern and source. Okay, and again, we're involving a pointer in this particular example. But if you look at the actual algorithm, the search algorithm, you see that we have source plus the size of the array itself, and then again repeated we have pattern and then the size of the array, okay, or the number of elements. And then we're doing this comparison with the if and the else statement. Okay, so if pointer equals source plus 9, no match found, else match at where it's located. Okay, so when we run this, we see that match at 3. So you can see that the source at 3, and here is what this final output is saying, match at 3. Okay, so 33 is the only time it's actually, that's the first time it's actually being matched. Okay, one last thing I'd like to point out with all of these examples is that in each one of them, we had this include algorithm. So if I want to access all of these algorithms, I actually have to have the library algorithm that's contained in the STL. So this is where it comes from. This is how. So if I tried to comment that out, there's no way I'd be able to actually use the search algorithm, and you can see it gives me the red line underneath. So it's important that you include that. So whenever you do see the pound include for the algorithm, you know automatically you're in the STL, and you know that somewhere inside that code there's likely to be algorithms that come from the library itself. Iterators are pointer-like entities that are used to access individual data items, which are usually called elements. In a container, often they are used to move sequentially from element to element, like you saw with the array. It's a process called iterating through the container. You can increment iterators with the ++ operator, so they point to the next element, and you can dereference them with the asterisk operator to obtain the value of the element they point to. So in the STL, an iterator is represented by an object of an iterator class. Okay, so we'll look at that as an example when we get further on. And There are 5 different things going on here, 5 different types. There's the random access, and it can go forward and backward, as well as the bidirectional. But then there's the forward iterator, the output, and the input iterators. We don't have to spend too much time on this right now, but when we get into the code example, we'll see an iteration where we plus and we do a minus minus. So I want to talk a few potential problems with the STL. Sophistication of the STL's template class places strain on compilers. So sometimes it's hard to find errors because the compiler reports them as being deep in a header file, where they are actually in the class user's code. Pre-compilation of headers, which speeds up compilation dramatically on compilers that offer it, may cause problems with the STL. And then finally, the STL may generate false compiler warnings. You can think of vectors as smart arrays. They manage storage allocation for you, expanding and contracting the size of the vectors as you insert or erase data. You can use vectors much like arrays, accessing elements with the square brackets. Such random access is very fast for vectors. Okay, it is also fast to add or push a new data item onto the end or the back of the vector. When this happens, the vector size is automatically increased to hold the new item. The pushBack member function inserts the value of its arguments at the back of the vector. The back is where the element with the highest index number is. The front of the vector, the element with index 0, unlike that of a list or a queue, cannot be used for inserting new elements. So what you're simply seeing here is if I want to add to the vector, I push it to the back, and if I want to remove, I pop it off of the back. Okay. So these functions, this pushback and pop off, become very common things when you're dealing with vectors and lists and deques and stuff like that. So they become extremely important functions to understand. So in this particular example, because I want to use a vector, I need to put the vector include. And what we're going to demonstrate is the pushback, this operator, and size. Okay, so I've declared my vector right here, and this is the syntax that we looked at earlier. And all I'm simply doing is, if I want to put values at the end of the array, I call the pushback and I add the actual value. And I can continue to do this. So what you see here on these two lines, 16 and 17, is I'm saying replace my first one and replace my last one. Okay, so notice here I've got 4 elements, and that's what this size function does here. It determines, or it tells me, the size of the actual array. And in this case, there's 4 elements in this array. And now I'm just cycling through to see what's in there. Now remember, we're not going to see 10, 11, 12, 13. We are expected to see 20, 11, 12, 23. So if I look at the compiled result, that's exactly what we're getting. Now the reason we're actually able to see that is because of the overloaded operator with the square brackets. So this is just typical in an array, but I wanted to make special note of it, that if you're trying to print out what the result is or the values inside an array, that's the syntax that we would be using right now for this vector. The next example we're going to get into is the list, but we're going to do a much longer example at the back, but I want to take this opportunity to introduce it. So an Stl List Container is a doubly linked list in which each element contains a pointer not only to the next element but also to the preceding one. The container stores the address of both the front or first and the back or last elements, which makes for fast access to both ends of the list. We push data on the back, the end, and front of the list in such a way that when we display and remove the data from the front, it's in normal order. Okay, so the push front, pop front, and front member functions are similar to push back, pop back, and back, which we've already sort of seen with the vectors. Lists are appropriate when you will make frequent insertions and deletions in the middle of the list. This is not efficient for vectors or deques because all the elements above the insertion or deletion point must be moved. So you can see what's happening here. However, it's quick for lists because only a few pointers need to be changed to insert or delete a new item. However, it may still be time consuming to find the correct insertion point. Here's an extremely simplified version of a list. But before we begin, note that on line 4, I've got a #include for list. So that gets that goes into the STL for list. So if you look at this line right here, it says list int ilist. So this is our template. That's telling us that we want to do a list. And if I want to push items onto the back, I do push back 30. Here's another example, push back 40. And if I want to push an item onto the front of the list, it's push front 20, push front 10. Okay, and then I have this little setup here, the number of items. So I call the size function on the ilist. That's what I'm initializing size to. And then I run this for loop, and you notice here I call the front function. Okay, so I'm reading the item from the front and I pop item off front. Okay, so then I'm just cycling through there so that I can actually print it to the screen. So what this little program did was it printed out 10, 20, 30, and 40. And notice that it's in numerical order, even though what we wrote in functions was push back and push front. You see that it came out in the proper order. Now the interesting thing is that as the compiler goes from the top to the bottom of this, it's pushing this to the back, then it's pushing another one onto the back, and then it's pushing front at the front, and then on top of that it's also putting the 10. So it may seem like it's been sorted, but in actuality the way we wrote this sequence, or from line 11 to 14, we actually input this in numerical order. A deque is like a vector in some ways and like a linked list in others. Like a vector, it supports random access using the brackets operator. And when I say brackets, I mean the brackets that you would expect from an array. However, like a list, a deque can be accessed at the front as well as at the back. It's a sort of double-ended vector supporting push front, pop front, and front. Memory is allocated differently for vectors and queues. A vector always occupies a contiguous range in memory, meaning it's very linear, always starting at the 0 element. If a vector grows too large, it may need to be moved to a new location where it will fit. A deque, on the other hand, can be stored in several non-contiguous areas. It is segmented. A member function capacity returns the largest number of elements a vector can store without being moved, but capacity isn't defined for deques because they don't need to be moved. So don't worry too much about capacity, just know that it's another member function. Okay, so let's go over to Visual Studio and have a look at a practical example. So here you can see that we're doing a #include on a deque. Okay, and everything else for the most part looks relatively similar, with the exception of this syntax. So it's deque being a keyword, same sort of template, right? And then we're calling it deque int deque. Okay, so we're doing a push back, a push front. And very similar to the last example, but see here we changed the middle item in the second element, or in the third element actually, to 33. Okay, so we've already seen examples of push back, push front, and the this operator here. They work the same for deques as other containers. So as you can see, here's the output, okay, of all of this. So it's 10, 20, 33, 40, and 50. But notice above we did it this way, and then we just added in the 33, okay? So what I'd like to do is look at an example of using a vector to do a add to a contact list. So you can see here that this vector is sequential. It starts at 0, goes to 5. So it's actually contiguous memory, okay? So let's say I want to add Brian to the list. Okay, and clearly Brian in alphabetical order fits between Audrey and Cheryl. And so what I would have to do with the vector is come up with some programmatic way of adding another element, moving Tom over. Then I have to move Steve over, then Mike, then Greg, then I have to move Cheryl, and now finally I can actually move Brian up into the position that I want. Okay, so what happens if I want to delete somebody from the contact list? Okay, so now I want to delete Mike, and I can take Mike out, but now I have to move Steve back over, then I want to move Tom back over, and then I've got that final element in the array to deal with. So you can see that programmatically this is going to be one thing. In terms of processing, it's going to be another, because that is not going to be very fast. I could have hundreds of contacts in my application. I could have thousands or even millions. So it's not going to be that great to do this as a vector. I want to do this in a more appropriate manner using a linked list. Okay, so an issue that I may have, like I said, is that I could have 100 or 1,000 or even 1,000,000 contacts in my list. So what I would do is create a series of nodes. Okay, and what you're seeing in this node is some data and a pointer. And we're going to replicate this node with the pointer as we go, as we continue to add more and more nodes or data points to our list. Okay, and then finally we get to the end and we're going to terminate it with a null. Okay, so it's important to understand that this is non-contiguous. It's not like an array where it has to be in a sequence starting at element 0 and continuing on. This can happen all over the place. Okay, so if I want to put Brian in here, we're looking at a different scenario altogether than, say, a vector or a normal array. So a point that I'd really like to make here, talking about the array or vector versus this linked list, is that the vector or the array, like I said, is contiguous, meaning those items. So for example, if we're using Audrey and Cheryl and Greg, if we put them all into an array, they would be right beside each other. The first element would be where the address is being held. Okay, but in this particular case, the way these are linked together is through this pointer. Okay, so each one of these nodes actually has a pointer. So what this implies is that Audrey's memory address could be completely in a different area of storage than, say, Greg's. Okay, so they're not contiguous. It means that all throughout your memory inside your computer, Audrey could be addressed at one location. Greg could be addressed at a completely different location somewhere else. Steve, again, would be at a very different memory address in your computer. So it's not contiguous like an array or a vector. You're storing a bunch of variables and you're connecting them all through pointers. And the way that they're connected is through the pointer in each node, through its memory address. So literally, Greg could be 1,000 or 2,000 memory addresses away from Tom, or even 1,000,000 memory addresses away from Mike. Okay? So finally, what you have to understand is if we are all linked through these pointers, if you get towards the end and you see Tom, Tom has to actually have something as well to point to, okay, because he's just a node. And so what we would do would be to have Tom point to a null at the very end, okay? So it's you don't want to have that hung pointer not pointing to anything, okay? So suppose I wanted to add Brian to this list. Okay, so the great thing about this is that I don't have to, like the array, try to move the values over to the right inside my array like I did with that vector. Okay, I don't have to slide everything down one by one. Okay, what I can do is reshape this, because what I can start to look at is if I want to add Brian between Audrey and Cheryl, the next thing that I should be doing is now moving Audrey's pointer to the beginning of Brian, and then Brian's pointer to Cheryl. And by doing this, I've now successfully inserted Brian into my linked list. Okay, so that's pretty impressive in terms of computation when it comes to adding, let's say, 1,000,000 different contacts to a list. Okay, so that's much easier to do than programmatically trying to shift everything up and down inside an array. So one more thing to consider is that what happens when I want to start my linked list and I actually don't have any contacts in there. So I haven't even started with Audrey. Okay, so what happens is we create this different class, this head pointer. Okay, so if you consider that all the contact list names, they're like Audrey and Cheryl and all those are a separate class for holding the data in the pointer, enabling you to add to the list. You've got to actually have a way to start this list as well. Okay, so the starting point is where you're going to get into your head node. Okay, and notice that the head is actually pointing to the other class, the node class that's holding the name Audrey and the pointer. So I've got basically a head class that's going to be pointing to a contact class. Okay, so I've got my start point pointing to the very first sort of model or template of what all of my contacts are going to look like. And then finally, it's possible that you're going to have this tail node at the end as well. Okay, so instead of maybe going to a null, you're going to move the this final node around. But as we get into the actual program example, we'll talk more about this. But just to be aware, you've got your head, your nodes, and then a tail, which is really, for the most part, just pointers. Okay, so when we look at this sequence of elements, these are referred to as nodes. And the node actually has the data, but it also has the link or the pointer that can be referenced as nodes, or even in this case at the very end as a null. Okay, so we're gonna in the program check for whether or not we've got a populated node class or if it's just a null. So now if we just take a moment and we look at the node class itself, we're going to call this one contacts, and it's basically holding on to one piece of data, a name, and then it's also got the pointer to the next node. Okay, so this is kind of another example of how it's going to look in the program. It'll be from the class contacts, and it will have a string name and then the contacts pointer next. Okay, so it just kind of makes sense that we call our pointer next because we are pointing to the next node in the actual list. Okay, so why don't we go over to Visual Studio and start building this out. So what I've done is I've already actually built the entire software example, and rather than have you guys sit here and watch me type all this out, what I think I'm going to do is go through all the steps that I've gone through, and I'll supplement that with some slides explaining why I'm doing those specific steps. So right now what I want to do is just show you what this application does. I just want to kind of manage your expectation of what you're going to see in this particular video. But there are a lot of moving parts, and it's important, I think, to try to teach how to do this, that I supplement it going between some coding and some slides. But I certainly don't want to waste your time with me sitting there typing on the screen. So what I'll do is you'll see me go back and forth throughout the coding of this, just to explain certain concepts to make it a little bit more easy on you. So all this simply does right now is it's my contact list. It says enter the name of the contact or queue to quit. So I'm going to type in Tom, and it reprints Tom to me. Audrey. Okay. Madeline. Riley. Okay, so that's all it's doing right now, is just printing out what I'm adding to the actual linked list. Okay, so these are all nodes that I'm inputting into. And notice as I'm typing them in, they're being reprinted back to me in alphabetical order. So if I hit Q, okay, and it says enter the name of the contact to delete or Q to quit. So I'm going to delete Tom. And now notice Tom came out of the list. So next one I'm going to do is Madeline. Okay, so pull her out of the list. That leaves Audrey and Riley. Okay, so that's actually, that's everything that's going on. One more thing I'm going to do is Audrey. I'm going to delete her, and I'm going to delete Riley. And now I'm going to try and delete Tom again. Okay, and it says contact cannot be deleted from an empty list. So I populated it, I removed everybody, and then I tried to delete again from the same list, and I got a message saying that I can't delete anybody from an empty list. Okay, so what I want to do is I'm going to start off with the node. So when we're back here in this next class, I want to make this node class called contacts, and the only data members I'm going to put in it are string name and this contacts with the pointer next. Okay, so it's a lot easier said than done, but let's go back to Visual Studio and have a look. Okay, so we're back here in Visual Studio, and what I've done is I've created the project already, but I have this contacts.h and then my contacts.cpp. So I'm going to use my header file, okay, and I need this string here. But the member variables that I have in here are just the string name and then the actual pointer. So I'm actually using this inside of my data types. Okay, so even though it's contacts, it's perfectly legal to say, okay, that's my new type is contacts. Okay, and I've got this pointer next. So this function here is just my contacts constructor. Okay, and I'm setting my name to none until otherwise specified. Okay, so then finally here on this line right here, this is what I'm going to use to print out the information back to my screen. Okay, so it's not your typical cout, it's something different. And I'm going to come back to this line after we build the next class. Okay, so because it's something that is going to cause problems if I don't have this in here, but I don't want to explain it to you just yet. So when I go back to my implementation, simply I've got these two functions. I've got my contacts, and I'm just passing in the n for my name, and I'm setting my pointer next to null right off the bat. Okay, so when I go back to here, I'm setting that to null. And of course, make note of the fact that here I've got the asterisks, but when I actually use it, because I've declared it here in H, but when I go to implement it, I don't have to actually add the star, it's redundant. So I'm just setting those to an initial state right now. And then this here is just what I'm going to print out to the screen with whatever the result is going to be. Okay, so that's the way I'm doing that. It's an operator overload, and it's an O stream in two cases. Okay, so we'll be passing in the C, and that's how it's going to pick up the name. Okay. Currently where we are is we've just created this contact node. Okay, and we can instantiate a whole bunch of these contact nodes if we really wanted to. But at the moment, I don't actually have a way to link all these things. Okay, so they're just nodes out there that I've instantiated, but I'm not actually connecting them yet. What we should be focusing on now is the consideration of this head pointer. Like, we can't actually start a list yet. We don't have a starting point. We just have a bunch of nodes. So in order to get those, we have to have a starting point, which is going to be our head. And then we've got the contacts. Okay. So what I'd like to do next is get into this list class, this new class for the head object. Okay. And then we'll be able to start linking things together from there. So let's go back to Visual Studio and start working on the list class itself. Okay, so I'm back here in Visual Studio, and what I'm doing is I've got two new files here in a new class, and this class is called Contact List. Okay, so this is where my head pointer is going to be. Okay, so what I've got is my contact with the head pointer. Okay, and it's going to be part of contacts. And you'll see here, even though I'm in the contact list.h, I'm including my contacts.h so that I can get this here. And this pointer object right here, head, is what I'm really interested in, first of all, in this class. Now, I have other functions down below, but I'm just pushing them out of the way until we get through the first part of what I want to do. So I've got my constructor here, and then I've got this little function here, which is my add to head. Okay, so when we go back and we think of the slide, we're talking about the head pointer, and we're saying, okay, there's nothing in the link. Let's actually add a node to this. So I'm going to call this function to add the contacts node to my actual list. Okay, so when I go back to, I get into the implementation of this, and of course I've got more down there, but I'm trying to keep you focused. Notice I'm starting off with my constructor, and I'm just setting this all to more of a safe empty state. Okay, so size is going to be set to 0. Okay, because right now there's no, I want to do a count of how many items I have in my contact list, but there's nothing in there right now. And my head pointer, I'm just going to point it to null. Okay, so here's the issue that when I get into this add to head. Okay, so I'm just passing the name. That's all I'm doing, because you saw me in the beginning. I just typed in the name, say Audrey or Tom, to begin with. Okay, so what I'm doing now is I'm going to create this new contact. Okay, so I'm going to call the contacts class, and I'm going to call it new contact, and it's going to be a pointer. Okay, so in this pointer is new contacts. And I know that you're not seeing the keyword delete anywhere in this right now, but I don't want you to be concerned about that right now. We're going to get to that when we start deleting nodes, okay? But for now, just know that in order to add that new node onto my list at my head, this is the syntax that I want to use. So then I want to get into a comparison. Okay, so what I'm going to say is if head equals 0, then go ahead and assign new contact to head. Okay, so great. Now we're good. Else, if there's already a node in the list, then add the head to this new contact and point to this next. Okay. So, and then we want to assign this new contact to back to the head. So in this case, I'm using size as a, it's just basically to count what I'm doing. Okay, so we started off at 0, and I'm going to increment that every time we create a new node into the program. Okay, starting here, you can see at the top here, I'm just putting just a title on this. Okay, and then the next thing is, what I'm saying is, give me, instantiate this contact list 1. Okay, that's my new list. So give me a new linked list, okay? And I've got my string name, and then I'm going into this while loop right here. So these comments here, just ignore those for now, just focus on the add to head. Okay, so they're coming later in the video. And so what I've got is my cout statement saying enter the name of a contact or queue to quit, a cin, my name, and then this little if statement, so that if my name equals queue, I break out of the cycle and I'm done. Okay, but if I type in a name, then pass the name of what I'm typing. So Tom would be passed into this add to head function in my contact list 1. So that's all that's happening really right now in main. Okay. So let's go back and see a little bit more in the slides of what's really going to go on next. So at this point here, we've got our head class, and now we've got our contacts class, our nodes, and this is what we're able to do, right? We're able to just add new contacts to the list, and that's it. In this scenario, what happens is we've got the node here, okay, and we've also got this. We're going to put this new contact pointer in there. That's just our normal node, and the new contact is going to point to the address of the first node, Brian. So we've got a scenario here where if null, it means that our head is not pointing to anything. Okay, so it means that we have an empty linked list if our head is pointing to null, and in this case it's pointing to null. But let's say we do want to add this contact. So the simple thing that we need to do is actually move our pointer from the head over to the address of the node where Brian is. Okay, so new contact and head are both pointing to the same memory address. Okay, and one thing to note is that when we finish with that function, the add to head function, new contact goes out of scope and dies off of the stack. Okay, so that's no longer there. So then we get into another situation. So let's say we've got head, and head does not equal null. So it means we've got at least one or more, or a minimum of one node in our linked list. Okay, in which case it happens to be Brian. Okay, so now we want to add Sarah into our linked list, and notice 0x30 and 0x60, they're not contiguous space, they're totally separate memory addresses. So what happens here now is that Sarah wants to get into the list. So we've got the new node for Sarah, okay, and it's also going to point to the next node in the list. Okay, so now you have head and Sarah both pointing to where Brian's node is. Okay, so what needs to happen is now we can just see that the new contact will fall off. Okay, and head now points to the address of Sarah. Okay, and thus begins the cycle again if I want to add more stuff. So what I want to do is go back to Visual Studio and start implementing what's happening there in those parts of the code inside that function. So here we are back in this add to head function. Okay, and I'm just passing name, and I've got the contacts in there. So my first condition is my head equal to 0 or to null? And if it is, then assign new contacts to equal head. And remember, this is a pointer we're dealing with. These are both pointers that we're dealing with. And else, then assign head to this new contact next. And then new contact will be assigned to head. Okay, and we're adding one, so right here with the incrementer, we're adding that plus plus. So that's really the behind the scenes of what we're trying to achieve with that particular function there, that add to head. Okay. Okay, so Let's assume that now we have started to build out a bit of a linked list and we want to traverse that list to look at the data. Okay, so we're kind of set up in this construct for a minute here. But one of the things that we need to talk about is when we move these pointers is that, let's say for example, I've got my head node going to a data node and I've got this pointer. Okay, so there's a certain syntax that we have to use in order to access that data because head is a pointer. So I need to have this little dash with the angle bracket, and it creates an actual arrow that's pointing. That's syntax for dealing with pointers. And conversely, there's another way that I can do that as well. I can do a asterisk with head. It's got to be in the brackets. And then I've got to call the dot operator on the data. Okay, so both methods will produce the same result, but they're just syntactically different. For me, it seems a little more easy or even intuitive to use the first example because it looks like you're pointing from head over to data. So another thing to consider is suppose we want, we've got head pointing to the first node in this linked list, but suppose we want to actually point to the next one. Okay, we could syntactically say, okay, let's go with, we could do this. We could say head, point to next, and then that next is going to point to data. Okay, but that becomes a little bit cumbersome because if I want to go into, say, the third one, okay, if I want, say, the third node here, then I would have to do head, next, and data. Okay, so that's not really the most intuitive way of doing that. So I think that's not something I definitely want to do. Okay, but instead, we can do something different. So if you look up here, what I can say is I can use the pointer head to next and then assign that back to head. Okay, and that I think is a much better way of doing this. So if I look at it this way, I'm just moving head over to the next data. Okay, that's really what I'm performing there. This head here now points to this 600 address. Okay, so what I'm saying is when it was previous to this, when it was in this situation, what I was saying was head's next here, right there, is now going to point to here. Okay, and a point I want to make is notice the addresses. That's just to kind of illustrate that we're non-contiguous again. This 600 is a different memory location than this, which is not in any sequential order of any kind. Okay, so this actually presents a bit of a challenge to us in this particular case. And the reason is once we've moved that head, we actually have no way to get back to this location. One of the things I can do is create this traversal pointer. Okay, so the traversal pointer I can move along as well. And what that would be this traversal pointer will point to traversal pointers next will point to the next traversal pointer. So what it does is it actually will skip along to each node, okay, and it'll just keep going as we go. And the dots there just to say that it's an indeterminate amount of nodes inside the linked list. Okay, so what I've got here is this syntax for this is while my traversal pointer is not null, then do some other operation and then take that code there, that traversal pointer to pointing to next, and then assign it back to the pointer. So in this particular context, you can kind of think of it as mountain climbing. Okay, the head pointer is going to be your safety line, and the traversal pointer is going to be your advancing line when you're climbing. Okay, so when I traverse that pointer, I never lose contact with my head pointer, and my head pointer is always at the front of my linked list. Okay, so it's important to understand how that's actually working. Okay, so the last thing, when I want to go back to this really quickly too, and I want to just emphasize the fact that I'm traversing Okay, so while my traversal pointer is not equal to null, which is this here, just to keep going through the linked list. When you reach null, then you've met that condition. Okay, so that's why I've got the null in there. I'm getting to the end of my linked list. So if we go back to Visual Studio, what I've done is I've added this list here, this print list. And what I'm doing is I'm simply just assigning the head to traversal pointer or traversing pointer, whatever you want to call it. And one thing I want to do is I do want to update that because I don't like that syntax. I do prefer that my asterisk be assigned to the variable name. And Visual Studio will like to actually attach the asterisk to the class name, but I don't really like that syntax. Anyway, it's just a preference. So now we get into this while, and so why my trav PTR or trav pointer is not equal to 0 or not equal to null, then this is what I'm gonna output my pointer value and then do this assignment. Okay, so that pointer pointing to next, and then assign it back to the pointer. So that's what I'm going to do there. And notice I don't need a for loop for this. Okay, it's an important thing that you understand. I don't need a for loop because I'm not dealing with an array. Okay, I'm traversing in a linked list. I'm not traversing an array. It's a very different thing. Typically when you have an array, you're always going to have a for loop. Okay, but in this case, that's not what we're doing. And just to be clear, I went back to my header file and I've actually put the function prototype in there. Okay, so traversing the linked list is right here. So I want to make sure that I bring up something that I promised to talk about earlier, and it's this next pointer, because we use this next pointer here and then again in the new print list function. And that is back here on this line here. It says need this to access our pointer, our next pointer. Okay, so without this friend class, when I get over to the implementation of this, I can't see this next variable. So it's vital that I actually open it up by using that friend. Okay, so that's what that line is for. I know I said I'd come back to it and I just wasn't sure if I did. So the last thing I want to talk about in this file before I continue is that when I go back to my main function, I've got this add to head. So I'm calling that function that we had previously done. And then right below it, I'm going to do this, I'm going to call this print list on my CL1. So my contact list 1, I want to now print it out to the screen. Okay, so in this case, what I've done is I'm just calling this add to head, and then right after that, I'm saying, okay, print it out to the screen. Okay, so that's all I'm simply doing at that point. So I just want you to ignore what's below this line here, because we're going to also get into that when we start doing the delete operations. And just as a handy tip, something for Visual Studio if you didn't know, if you want to know how a function is actually implemented, you can put your cursor over it and then do peak definition. And you can see that it actually opens up just that window into my contacts.cpp and allows me to see how that entire function is implemented. So this add to head, and I'm passing in name, that's everything that's going on in that function. So that's more of a tip than anything else. So let's move on and see what we have to still do. So in actuality, when I do look at this, I would have wanted it down here first, but I'm gonna continue to work on this, or I did continue to work on this. So what happened was I put it in there, but for the time being, I'd be satisfied if you're following along on the computer that you actually are to this point in your code, with this print list being called outside of the while loop. Okay, there'll be time soon enough to put it back in there. So the next thing that I want to do is go ahead and insert a node into an established linked list. Okay, stuff that's been populated already. Okay, and you can see here, let's suppose I want to insert Peter. And now I know alphabetically Peter needs to be inserted between Mike and Steve, okay, because I want to maintain that alphabetical order. So I can't have my new node going to the front of the linked list. I can't have my the Peter interacting with the node for head in that pointer. Okay, so I want to be able to insert this in between the node for Mike and the node for Steve. So what happens is I've got 3 possible cases that can happen. Okay, so I can insert a node into an empty linked list. Okay, so that's really not a problem, and we've done that already previously. And I can insert a node into a linked list that has at least one other node. Okay, and then finally I can insert a node into a linked list that has at least one node or more, but we don't want to add it in at the head of the linked list. So that's really where we are right now by this particular scenario with Peter. Okay, so insert a node into a linked list that has at least one node or more, but we don't want to add it at the head of the linked list. So we've got this particular scenario. We want to add Dan in, but we don't want Dan at the front of the list. So we have this current pointer. Okay, and what we're going to do is say, does Dan come after Brian? Well, the answer is yes. And then we're going to do it again and say, does Dan come after Cheryl? Yes, the answer is yes. Okay, and then finally we get to Greg and we say, does Dan come after Greg? Well, the answer there is no. Okay, and what I can't really do, and I'll tell you why in a minute, is I can't just say, all right, let's start manipulating pointers everywhere. Let's have Cheryl's pointer point to Dan, and then Dan's point to Greg, and then Greg carries on. And the reason is that when I do that, I have, again, no mechanism to hold on to Cheryl again. So I'm actually losing my safety line, which is why I said before in the analogy of mountain climbing, I'm losing my safety line. So I have no way to go back to Cheryl. So, you know, I'm in this situation right now, and what I can do is let's start over. Let's go to the start this process again. And I'm going to go back to current, and I need to add a new pointer called previous. Okay, and right off the bat, I would initialize that to 0. Okay, so now I've got previous that's going to point to Brian as well. It's initialized to 0, but then I'm going to eventually have it point to Brian. Okay, so then I'm going to check my current, and I go to Cheryl. Okay, and then what happens is right after that, I follow with previous, because as I'm traversing along, current is the new one, but the previous one was the node right before it. I know that's a little bit confusing. Okay, so then I start to think about, all right, what about my new node? So my current becomes, or sorry, new node's next becomes the current. Okay, so what that ends up meaning is that I'm no longer, my new node Dan is no longer pointing to null. Okay, and what's happening is Dan now points to Greg's next. Okay, and then my previous next becomes a new node. Okay, so what that means is now I move over my previous, and I've got Cheryl pointing to Dan. So I've always got a handle on, my analogy with the climbing. I've always got a safety rope, and I've also got a main rope. Okay, so here I am, and what I want to do is now go back into Visual Studio and look at the code for this. Okay, so I'm back into my contacts header file, and I'm going to add this this function here, insert into the linked list. Okay, and that's just called insert. And again, I'm taking my string. So when I go to the implementation of this one's a little bit more involved. This one here has a couple of different conditions that are happening. Okay, and the first one we had was case 1, where we had an empty list. And then this one was we insert into the head and it's not empty. and then we insert anytime after the head, okay, which is not empty. So in the first case, it's empty. Then as we go along, we've got the flexibility at the head, or if we want to do it somewhere in a different spot. So really quickly, what I'm doing is I'm creating. All right, so right off the bat, what I'm going to do is construct a new node. That's the first thing I'm going to do. And once I've got the new node, then I'm going to say, okay, is my head equal to null, right? And if my head is equal to null, then set the new node equal to head. Else, come down here. And this is where we're making our current pointer and our previous pointer that I just previously explained. Okay, so we need to traverse the list to find the insert location. So while current is not null, then perform this operation right here. Okay, so the current's name will be greater than or equal to new node's name. Okay, and if that's the case, a break. If not, then we're going to set the current to previous, and then current's next is going to be set to current. Okay. I know it seems a little confusing, and I hope you appreciate why I kind of went through and did all this, these slides, and I kind of animated them so that you get a better understanding of what I'm really trying to do. Okay, so in case 2, what happens is insert into the head. So I want to put this at the front of the list. So if current is equal to head, then what I'm saying is new nodes next will be now set to head. Okay, and then head will be set to new node. Okay, then finally the last piece to this is going to be insert after the head. So somewhere in the middle, say, for an example. I'm going to take new nodes next, and I'm going to set that to the current, and then the previous next goes to new node. Okay, and then finally we're going to end out this with an incremented size. Okay, so the size of my linked list is getting bigger by at least 1. Okay, so that's a lot. Do we make any changes to the main function? So if I go back to main and I have a look in there, it looks like at this point, what I want to do is right here in that first while loop. Okay, I'm asking for the name of the contact or to quit. And if it's a queue, I break out. If not, now I'm going to call my insertion function. And my insertion function is what's handling all 3 of the cases that we discussed. And it comes up with an appropriate response for all of them. Okay, so let's keep going and see what else has to be done. And I suspect it's finally the delete. So let's have a look at kind of how a delete goes together, and then we'll come back to the code. Okay, the delete a node from a linked list is probably the easiest part that we're going to do, but you may have in previous parts of this video been asking yourself, okay, you used the keyword new, but when's the delete going to happen? The delete kind of happens a little bit different, but we're going to do it in this area here. So I want to delete Audrey. So the thing that I want to do is I need to move the pointer from head. So head's next is going to have to move to the next node past Audrey. Okay, so head will now be the equivalent to Cheryl's next here. So that's what head is going to be pointing to next, and that's what we assign to head. So all that really means, this line of code, what it does for us is it just stops Audrey's next from pointing to Cheryl's next. Okay, and then simply we call it a delete on the current pointer. Okay, so then that goes away. Now we've got another situation. Let's say we want to delete Greg. Okay, delete somewhere not at the head of our linked list. So what's happening here is that you've got the previous pointer and the current pointer. Okay, and you're going to set the current's next to previous next. But basically this is what I want to do. I want to have Cheryl bypass Greg and go right to Mike. Okay, so I've changed my Cheryl next pointer to be pointing to Mike's next. So then I just do delete on the current. Okay, so there goes Greg. That is now gone. And I've maintained the integrity of all my pointers. So finally now we're getting into our delete node. We just looked at that on the slides and now we're actually going to do it practically. So I'm in my header file and I'm just passing in, it's the same parameter that I'm passing in for all the functions above, except for print list. So let's go to the implementation of that. Okay, and here it is. So there's a little bit of work to do here. I know I made it sound a lot simpler than it is, but for the most part, it's quite similar to what we're doing up there. We're just deleting stuff instead. So in my first scenario, I've got an empty list. And so if my head is equal to null, if it's pointing to null, then contact cannot be deleted from an empty list. So if there's no name, I can't delete a name. That doesn't exist. Okay, so then we get to else. Okay, so if there actually is a name, then we're gonna, this current pointer is gonna point to head, and then previous is going to point to null. So we need to traverse the list to find the node we want to delete. So in this while loop, what you're seeing here is if my current is not equal to 0 or equal to null, okay, then I go into this if, which is my current's name has to be equal to name. And if that's the case, then we break out of that loop. But if not, then we're going to set the current pointer to the previous pointer. And then we're going to set current to the current's next pointer. Okay. Now, in this next case, we've got a node with name not found in the list. So instead of typing in, I've typed in the name Tom, but I try to delete Mott, M-O-T, instead of T-O-M. So what it says is, if the current is not equal to null, contact with name, this Mott in my example is not found. Okay, so else, delete from the node. Okay, so now I got to check the condition again. Is my head equal to current? If so, head's next will now be assigned to head. Okay, and then case 4 is delete beyond the head node. Okay, so this is where now current's next will be assigned to previous next. Okay, and then finally, after all of that, I want to delete my current, and don't forget you want to decrement. Okay, so we're doing a deletion here. So my linked list is getting smaller by at least one node. So I want to decrement that. Okay. So there's a lot going on in this last function, and what I'd like you to do is maybe back up the video again, and what I would suggest is that you do this code, type out this code, then go back and look at my video and the previous slide part and see what was going on with all the pointers, so that you fully understand what I was doing here. Okay, there's no point in me running through yet another review of it. Just use the power of recorded media and go back and forth between the two. Okay, so now I'm finally going to get to, I go back to my main. And what I'm doing now is, until this point, all this while loop was in order to add things to the actual linked list. But down here, what I've chosen to do is, I'm going to do another while loop, and I'm going to say enter the name of the contact to delete, or Q to quit, right? So I'll just C in the name, and if it's Q, then I break out and I'm done, I quit. But if not, then I'm going to call the delete function on my linked list. Okay, and that's all I'm doing right there. Okay, and then just for testing purposes or whatever, then you can go ahead and print your list out. And then this is one final testing. Really cannot spell. Okay, so it's one final look at what the final output is going to be. So what I would do right now is compile that and test it out. So now I've compiled the program and I'm running it, and what I'm going to do is just test it out like I did before. So I'm entering my name, Tom, Audrey, okay, Madeline, and finally my son Riley. Okay, so I've got Tom, Audrey, Madeline, Riley, and now I'm going to quit, okay, and get out of that. And you'll see that it's actually printing my name a few times, and that's because I've moved around this print function that you're seeing, the print list function. I've done that a few times. You can play around with your print list function as well. So now I think what I'm going to do is just type in Tom. Okay, I've deleted Tom finally. I'm going to delete Riley. Okay, now I spelt that wrong, and now look, enter the name of a contact. Contact with name Riley with a U, not found. Okay, so we'll try to delete that again. Okay, so it deleted it. And you can see that the list is actually outputting a little bit shorter now. Okay, let's go with Audrey. R-E-Y. Okay, I've deleted Audrey. Who else do I want to delete? And I guess Madeline. Yeah, okay. So let's see if I go to quit. Okay, and that's my final output there, right? So it's not doing it the first time I demonstrated, just for the fact that I've added the print list function in a whole bunch of different locations, but it's still working. So I'm gonna try and run this one more time. And what I want to do is Q, okay, and then I'm gonna delete Tom. Okay, so there it says contact cannot be deleted from an empty list. Okay, enter name of the contact to delete or Q to quit. Okay, so that just about does everything for that particular linked list. And there's a lot of moving parts to this, okay? And I think that if you were to get in and do some practicing, it's going to be confusing as hell at the first couple iterations of this. But give it a honest to God try and match it up to what I'm doing. Now, the last hint that I can give you is just like I did in the first video, I said if you're confused about pointers, then draw this out and literally draw it with a pen and paper. Okay, same sort of thing here. If you want to do that, it's going to help you to learn this. When I learned linked lists, I actually learned them with sticky notes. Okay, I drew on sticky notes and I can move them all around. So I knew what I was pointing to. Okay, so you know, try to be a bit creative on how best to learn this stuff. But if you're great at visualizing it in your mind, all the power to you. That's great. So there's a lot of stuff I've thrown at you in this particular video. Thanks for watching. I hope it helped. And, you know, get in there and start practicing with linked lists. But it's important that you understand the foundation of what you're actually trying to do. Okay, so thanks for watching, and I'll see you in the next video.